Right, so introduction to machine learning. My name is Akinkunle, and this deck will be shared with you at the end of this class. So a few things I'm going to cover today. There's a lot to cover. I'm trying not to, just dump everything on you. I want to suggest it's going to be split into two parts, right? Where we'll get to a particular point, we'll stop for a break. It could be maybe 10, 15 minutes. Because the second half is going to be heavier than the first half. The first half is just to introduce it, right? So go through some introductions, ML terminology, ML approaches, something I call walk in a straight line. It will become obvious why I named that when we get to that section. Linear regression, squared loss, training and test sets, something called gradient descent, and overfitting and regularization, right? So it's quite a packed thing. So we're going to get there. Right. So machine learning really is, you've heard it a lot. I mean, it's not new. Everyone has, I think it's been the rave of the moment for a few years now. Particularly now when things have really blown in that space. So machine learning actually just allows computers to acquire knowledge from data without explicitly programming them, right? So traditional programming, if you want to do anything with computers, you need a programming language, you write code, you need to instruct the computer on what exactly to do and what to follow. It's different from machine learning. You basically just give it a bunch of data and it figures out how to actually identify patterns from the data you have, and then use that data to make predictions, right? That is simply what machine learning is, right? So before we go on, this is going to be one of the first questions I'm going to ask, right? Why do we use machine learning? I need people to get off, maybe two people. Why do you think we need machine learning? Like, why do we use it? Do we have any volunteer on the call? I'm going to, so that I can see the participants. Do you have any volunteer on the call to tell us why we use machine learning? If not, I'll just skip to the next call. That's also fine.
So I would like to give it the shot.
Yeah.
So we use machine learning to find the relationships between the features, like the features and the predicted variable we are trying to get. So what I mean in essence is that, for example, if we want to get the estimate of houses in a particular area, we can take in some features like how many bathrooms the houses have, the lot size, and what have you. And we combine these variables together to be able to predict, okay, what are the prices that this house would be worth? So that's my understanding about.
Yeah, thank you, Akinkunle. It's a good understanding. So I suppose my follow-up question to you is, that is absolutely spot on. My follow-up question is, why not do it manually then? Why do we need machine learning in this case? When we already have people, estate agents, people that value homes. Why do we need machine learning in this case? Do you know why?
Okay, my contribution as regards that would be that we need machine learning to, one, fast track this process and make more accurate predictions.
Yep. I think that's spot on. Typically, to fast track something that's an expensive process, you sometimes want to just make it quicker, maybe sometimes more accurate. Yes, not always, but yeah, sometimes more accurate than what you could do. So yeah, that's absolutely spot on. Thank you for your input, Akinkunle. So yep, I'll go back to sharing my screen. Yeah, so basically that's why we use it, right? So, and there are a bunch of applications, right? A bunch of applications we see in the wild, right? We know we have self-driving cars, which is quite popular, right? Anyone that's heard of Tesla autopilots, is one of the most popular ones in that space. If you have an iPhone, if you have a Google phone, they have digital assistants. You can say, hey Siri, it pops up. Oh, mine has popped up. Sorry, I wasn't calling you. You can say things like that, and that's an application of machine learning, because that takes your voice, get something and then does some task for you. Recommendation systems on apps like Netflix, right? If you go on Netflix, you see they recommend all these things for you. This is something, to Akorede's point, helps you save time. Imagine trying to do this manually, or with you want to write code for this. It's going to be almost impossible, right? So you use machine learning to build recommender systems for people. So it takes data of what people have seen in the past, and then you use that to actually predict what you think they will like. We have fraud detection. We also have spam filtering, different applications of machine learning, right? So again, before we go on here, I'm going to ask you, we're going to go back to the Menti just quickly, another 2 minutes. And it's basically this. And it's basically, when you think of machine learning, what words come to mind? So this is going to be like the mural of this session, right? At the end of this, I'm going to take a screenshot of this, send it to everyone. So when you think of machine learning, what words come to mind? Whatever comes to mind, just dump it here. Whatever clean word comes to mind, please dump it here. Cool. Features, yes. Validation, I like that. Test, train, split. Robots, yep. Some see them as robots, yep. Let's see, wait for more responses. We have automated statistics, intelligent systems, yep. Self-learning, that's a very good one. I like that one. Automation, absolutely. Finding patterns, yep. I particularly like statistics, because statistics in this field doesn't get the attention it sometimes deserves. So I like that one. AI, yep. GPUs, yep. So yeah, these are very good. I like how these things are coming together. But I spotted another one. Data, absolutely. I think that's the most important thing. The most important word here really is data. Over parameterization. Whoever put this has been reading a lot of textbooks. So nice. Regression, yes. Regression is something we will cover today. Ease. Interesting. So yes, thank you. 20 responses. We will share this. Thank you everyone for putting up what you think when you think of machine learning, right? So I'm going to stop this and go back to the deck. Right. So before we get into the reason I asked you for all those things, I want to actually make sure, see what people know about ML and all these things, right? So we'll cover a few ML terminology, right? A few things you should know about ML. And the first one typically is called a label, right? So someone put on that word cloud, prediction, right? Yes. Typically what you're trying to do with ML, like I described, is you're trying to learn from the data you have, a relationship that you can then use to make a prediction, sort of, right, in the past. So the label is the thing we are actually predicting. So it is often denoted by Y, right? And in many textbooks, in some textbooks, sometimes some people will describe it as a dependent variable or a target variable, right? So as it Ayomide that gave that answered the question about why do you use ML, it mentioned something about trying to predict house prices. In this case, the house price will be the label, what we are trying to predict, right, from our data. Right? So a feature, right? So we have a feature, right? So a feature is an input variable that we use for our task, right? So again, in the example that's I provided for us, it is what we are trying to use to predict what we're trying to predict, right? It's a variable we use to predict. It's what's in our data, right? So it is often denoted by X, and some textbooks call it independent variable. So that's something to keep in mind. So we have the label, we have the feature. In the example the number of bathrooms could be a feature, right? Something you want to use to predict another thing, right? So the model in this case is, the model encodes the relationship between the features and the label we're trying to predict, right? So at the end of everything, we come up with a model. You hear a lot of people say, oh, ML models. And essentially, they are just these beautiful mathematical things that encode the relationships, or the relationship between features and the label, right? So that's what a model is. And when you hear training, training, it basically means, that process where you give data to an ML algorithm, right? And you learn a model from it, from that data, right? So it's basically, you're training a model is you give it data, trying to get a model out of it. You're trying to learn that relationship. So there's something called inference, which is when you have a trained model, right? And you have a new data set, which maybe a new data set you want to predict on, right? You send that to the trained model and you'd be like, oh, what do you think this is? And the trained model would then tell you, oh, I think it is this, right? That's basically inference. You're running, some people call it predictions, but typically it's inference, right? So that's what that is. Cool. Right. So yes, so imagine this is very poorly designed, like a table, right? But imagine if you're trying to predict house prices, like Akorede, yes, it's Akorede. Akorede mentioned house price prediction, and I was like, has this guy seen my deck? I don't think he did. Right. So you have, what we're trying to predict here is the value of the house, which is our label, right? So, and there are features that you can actually use to predict the value of the house, right? So we have two features here, which is, for example, the number of rooms and the number of bathrooms. For this data point, obviously, one single row is a data point. There's one house. So you have number of rooms will be 2, number of bathrooms is 3, and the value of this house is 10,000. Could be dollars, it could be whatever, it doesn't matter. Right, and this is another data point itself, right, with another different house value, right? So you could feed this into an ML algorithm. Obviously, with more data, two data points is never enough. You feed it into an ML algorithm, and then it learns the relationship between the house value and these two features, right? That's for house price prediction. There's another type of prediction. Say your email, if anyone that uses Gmail or any form of email clients these days, it automatically can tell which email is spam and which one is not, right? So spam emails just go into your spam folder, right? So this is a feature, which is your email body, right? So hello, Alan. So imagine I get this email in my email client. Hello, Alan. Welcome to AI Saturdays. I know that it's not spam. This is the label. This is what we're trying to predict, right? And if you see an email like this, hello, you've won $100,000 in a raffle. It's more likely to be spam. Like someone is trying to be fraudulent with you. So it's going to be spam, right? So this is the label we're trying to predict in this case, right? So move to the next one. Right. So we've covered some ML terminology, something that we will need as we start getting deeper into these things and start speaking about ML. So there are a few approaches to machine learning, right? I'm very sure the person that puts over parameterization already knows all of this, probably thinks, why is this guy showing me this? But yeah. So we have supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning, right? Most of us, really, a lot of people tend to stay in this domain. Yeah, I think it's the most common one. I think it's the most common one. Unsupervised learning, I will explain it, but we don't have the time to go into it deeply on this call. Semi-supervised and reinforcement learning also. I'll just describe what they are. But these are the different approaches, different types of machine learning, if you like, if you want to call it that. Yeah, so supervised learning. In supervised learning, keep in mind, everything obviously needs data. In supervised learning, we use labeled data to train algorithms that are then used for inference. And the keyword here is labeled data. You label it. And what that means is, if I go back a few slides, right? The labels are this. We have given an example, right? Given a data point. We know what the value of that data point is, right? This is a label, well, obviously. So it's labeled, right? And that's essentially what supervised learning is. For you to train a model, for you to train in supervised learning, you use labeled data, which you have here, and the labels, right? You pass it to your machine, your ML model, and you use that to make predictions or inference at some point, right? That's supervised learning. The key is it uses labeled data, right? Cool, we're making progress. So that's supervised learning. The second one is supervised learning still. Now the supervised learning is now split into two types, right? Regression and classification, right? So regression and classification are two types of supervised learning. And the difference is in the label, really. In regression, what you're trying to predict, your label is numeric. It's a continuous quality. It's a numeric value like this, right? So this is regression, right? Because what you're trying to predict is a number. In classification, you are trying to predict a discrete label, like something that is not numeric, like categories. That is what you're trying to do in classification. So it's important to actually keep those two things in mind. Depending on the type of problem you're trying to solve, you need to know what type of supervised learning umbrella it falls under. So regression and classification. And we have unsupervised learning. Unsupervised learning is, as the name suggests, it's obviously the opposite of supervised learning. In unsupervised learning, we don't have labeled data, right? We just have a bunch of data points, right? We don't know where they belong to. We don't know which categories they belong to because we don't have that information, right? Either because it's too expensive to collect that information, or we just don't have, it's probably too expensive, or we don't have people to help us do that, right? But the absence of labels does not mean the data is not useful. You could use it for some other things, right? So one of the things you could do with unlabeled data is, you pass it into an ML model, and the ML model, for example, could help you cluster it. The ML model could look at that unlabeled set of data sets, unlabeled data sets, and find clusters within them. Look for similarities between data points and group similar ones together, right? That's the most common example of unsupervised learning, clustering, where you have a data set, right? And you're like, you know what? I don't know what labels this data points belong to. I don't have the labels. But you take it and actually figure out the similarities between them, cluster them for me, put them into groups that you think make sense, right? That is unsupervised learning, right? And that is what we do here. So there's supervised, which relies on labeled data. There's unsupervised that relies on unlabeled data, right? So depending on the type of task you are trying to do, you will use either unsupervised or supervised, right? We're going to go back to Menti. I'm going to ask a few questions, and perfect. All right, so let's present this. Word cloud is still up. Now, a question is going to come up, and I just want you, so you could join this thing. So this is the question. You have a data set containing images of cats and dogs, and you want to build a model that can tell you if a new image is either a cat or a dog. And use it. So we give this 1 minute. So 4 answers for supervised learning. Okay. What if people are wrong? I like Camille, I'm sorry if I did not pronounce your name properly. He said unsupervised learning. So if you don't mind, I'd like to, because most people put supervised learning. They may be wrong, by the way. So do you mind telling us, why you think it's unsupervised?
Hi. Supervised learning, because we have, you are trying to predict if it's a dog or a cat. So you already have like a label of the cat and the dog to train the data. Like that's why it's supervised learning.
Perfect. That's a good answer. Who wants to? I really want to hear from this person that said it's unsupervised learning, because it's brave to go against 16 people and think. Jack has raised his hand. Please speak, Jack.
So I'm saying that it is supervised because we learned that supervised, the data set must be labeled. So we have, because we have the cats and the dogs, already the data has been labeled already. Yeah.
Mm-hmm. Great. Yeah, so it's supervised learning, and honestly, the person I didn't label, yes, they are, because the dataset contains images of cats and dogs, and obviously you could infer, even if you don't have it, you could tag that. Yeah, and you want to tell, you want to build a model that can tell you if the new image is either a cat or a dog. So the outcome of the model itself is whether it's a cat or a dog. That's a classification problem. That's two categories: cat, dog. Right. So it's a supervised learning thing. Cool. We're going to go to the next one. So you have a data set of customer purchases, and you want to group similar customers together based on their buying habits. So you own a shop in Obalende, and you have data on your customers, and you want to group them together. Like, I actually want to see what customers are based on their buying habits. Really want to hear from this person. Okay. Yep, I didn't label. This question does not explicitly mention that the data set has labels. Maybe the data set contains the image. I mean, you could win in court if you argue this, but in my court, you are wrong. Perfect. This is very interesting. This is a very interesting split. 11 unsupervised learning. They may be wrong. This supervised learning people may be right. So who knows? So I want to know, the three people that actually said unsupervised learning for this, could maybe two people from this group tell us why? Oh, four. Okay, we have more. 4 people from here tell us why they think is unsupervised learning. And maybe 2 people from here tell us why they think is unsupervised learning. Let's start with the supervised learning group, please. If anyone wants to talk about that. Jack, yes.
Yeah, thank you. Because I'm saying it is unsupervised because we are not being told which kind of data the customers bought. We are only being told the history. So history there, the data is not labeled. So we have unlabeled data set there. That's why we are saying that it is unsupervised, because we are only dealing with the history, not the items which are.
Yes. Thank you for the answer. Also, I think you would have been teachers would have really liked you when you were in high school or secondary school. So, yeah. Does anyone want to explain why? One more person on the unsupervised learning camp, and 2 people from the supervised learning camp. Does anyone want to come up? Maybe one person from the supervised learning camp. I actually want to hear, because it's important to actually know why people chose this. Because the right answer is actually unsupervised learning. So I want to know why people chose supervised learning. So we can actually maybe correct that now.
Okay, I'm choosing like unsupervised learning because number one, we don't have like the outcomes, like the prediction, like how would I put it? Like a stated prediction from the data sets. And number two, we are grouping, like we are sort of like clustering. We are trying to group like different parts of the outcomes. So that's why I chose unsupervised learning.
Absolutely, that's spot on. So supervised learning, the people that chose it, just one person, please. If you don't have to come on video, maybe just an explanation of why you confused this for supervised learning, because we're just going to move on quickly after this. Does anyone know? Does anyone want to answer? If not, I'll move to the next question. Doesn't want to answer. But yeah, it's unsupervised learning because, yes, it doesn't have labels and it's grouping. So we want to group similar, we want to cluster similar questions together, similar customers together. So you want to build a model that can recognize handwritten digits. This should be very easy. Unsupervised. Mukhtar, yes, yes. Yeah. This is closer than I imagined. Okay. It's not unsupervised, right? Because what you want to do is you have a bunch of digits 0 to 9 that's handwritten in different writings, and you want to be able to say if looking at that a particular digit that's handwritten, classify it into one of these 0 to 9 buckets, right? So it's supervised. Last one. So you have a collection of news articles and you want to automatically bucket them into topics like politics, sports, and entertainment. Yep, answers are flying in. Really like this one. Unsupervised. Yep, absolutely. Yep. This is, I think it's the person is, yes, it's unsupervised because yes, we don't have labels for this one. We want to automatically bucket them, automatically group them into topics, into different topics, right? So yeah, perfect. So yeah, it is unsupervised. The reason I added that is I just want to make sure there's no need to rush these things if you don't understand the principles, right? Because I always believe like you need to understand the foundations to build anything solid on top of that, right? So that's why we had to do that, right? So yeah, supervised, unsupervised. We've done a bunch of tests. Most people got it. Hopefully the people that made certain mistakes can ask clarifying questions if they're not sure, or maybe things are clear now. So we'll move to the next one. Semi-supervised, as the name suggests, really is just a combination of supervised learning and unsupervised learning. So the data sets you use for semi-supervised learning contains both labeled and unlabeled data points, right? So you have your input data. Some of them are labeled, right? Some of them are unlabeled. You pass it to a machine learning model, and then it learns some relationship between them, and you use that for prediction, right? Or for inference. And reinforcement learning is it's a very different type of paradigm of building models, right? So it's basically based on rewarding behaviors and penalizing, behaviors that are undesired, right? So in general, what you have is there's a learning agent that is able to maybe walk around in an environment, right? Take actions, and then based on whichever action that agent takes, you penalize it or you reward it. So it's kind of like how we learn in the real world, how babies learn, right? So when babies are like learning agents because they are new in an environment and they don't know what is what, right? They don't know what's rewarding. They don't know what is penalized, right? So babies go around, they crawl, they touch a baby will see a candle and they'll be like, oh my God, this is fascinating. Crawl towards that candle, touch it, baby will be burnt. So the baby will realize that, look, that's not an action I should take. That's an undesired action, right? So the baby next time will know not to go near the fire, right? things like that. So a baby will see sugar and taste them like, oh my God, this is delightful. I love this. So that gives the baby, that's a desired behavior the baby will try to optimize next time. So that's basically what reinforcement. Yes, it's so I already said, I think the concept is called Q-learning. It's one of the ways of doing it. Yes, it's I'm not very familiar with reinforcement learning, but yeah, this is how it's stated, right? So we've spoken about supervised, unsupervised, semi-supervised, and reinforcement learning. Cool. So this is the second half of this. It has more content. You're going to have a few more math symbols. I tried not to load the slide deck with math symbols because, like I said, the goal of this is to motivate machine learning such that when you pick up a textbook or you pick up, you read a blog post that has more math symbols, things will make sense. You will be able to translate that, whatever you've learned here, and connect it with what is being said in textbooks or in your labs and all that, right? So walking the straight line, this equation should be very familiar to everyone. I mean, some people, I'm very sure, is even giving them, it's triggering them, taking them back to secondary school when in math class you were first introduced to y equals to mx plus b. Some say y equals to mx plus c, whichever one. So when you see this equation, what does it actually mean? Like, we know that m is called the gradient or the slope. B or C in some places is called the y-intercept, and we'll explain what that means. Y is obviously a vertical axis. X is a horizontal axis. And yes, equation of a straight line, that's what it is. So that's why I named this deck walking the straight line. Such a horrible name. So y equals to mx plus b, where m is the gradient or the slope, and b is the y-intercept. X is just a vertical, a horizontal axis, right? So if I go here, right. So these are two lines, right? These are two lines, right? And this one, for example, is y equals to 2x plus 1. And the y-intercept, basically, if you look at this line here, the y-intercept crosses the y-axis at this point 1 on the y-axis. That's why it's called the y-intercept. It is where on this graph, on this Cartesian plane, does our straight line cross the y axis. And it's here for this one, it's 1. For this one is -2. This one, it's here, and that's why you have it here, right? Obviously, this is the origin, and the slope or the gradient of this line is what? It's 2. Each of them, both of these lines have the same gradient, basically 2. And what's a gradient, by the way? Can anybody tell me? Can anyone get off the call and just tell me what is gradient in this? If you look at this line, how do you calculate the gradient? So someone put the y dx in the chat, Oluwafemi, which is correct. That is it. Yeah. So you've all answered it very well. There's a change in y. When you make a change, typically a very small change, but we don't care about that to be very precise here. But when you make a change in y, so in this case, you're changing x. So if you go so let's start from this point, which is what? On the y-axis is 0, on the x-axis is 1. And you go maybe from this one to this one, so 1 to 3. So the change in x is what? 2, because we've gone from 1 to 3 or 3 to 1, right? So yx2 minus x1. So this is our x2, is our new point, and is our x1. And then if we trace this line up at 3, if we trace it up, right, bam, when it reaches the line, the value of y at that point is 4. The value of y at this point is 0. So our y2 is, because our x2 is 3, our y2 is 4. and our y1 is 0. So that is 4 minus 0 over 3 minus 1, which is 4 over 2, which is literally 2. So that's the gradient. So at any point on this line, however you do it, however you calculate it, the gradient will always be 2. And if you do it for this line too, it's going to give you the same value, right? So the gradient just tells you how steep, how steep your line is, right? So, or how slopey it is. So let me give you an example. At the start of this call, I said I do not like hiking. I don't like climbing mountains because it's just so stressful. And if you're climbing, there are certain points that will have maybe just a little bit steep. The gradient of such mountains they're not going to be so much, right? And there are some other parts of the mountain that will just be like push up like this, right? So the gradient at that particular point is quite high. So you probably have a large gradient, right? So that makes sense. I don't want to belabor this point. We also have this. So this one, for example, does not have, these two lines do not have, they have y-intercept, but it's 0. And that's why both of them cross the y-axis at the point 0, right? This one crosses the y-axis at which point? Point 1. So that's the intercept of this one. And the gradient for this one is, so is the gradient of this one positive or negative? Like, is it a positive value or a negative value? Who can quickly tell me that?
Second one is a negative.
Yes, this one is both of these ones are positive because of how they are. But because if you make yes, it's negative. Because if you make a change along this axis and you go up, your y2 minus y1, which is the change in y, and your x2 minus x1 will give you a negative value, right? And that's why it's a negative gradient, right? So that's something to keep in mind. So yeah, this is, you understand why this is important now. Cool. And then that brings us to, keep in mind, I said we have 2 types of supervised learning, right? Regression and classification. For this class, we're just going to only talk about a regression because number one, it's one of those things that are quite easy to pick up intuitively, to understand intuitively. And then obviously classification, well, one form of classification, like one algorithm called logistic regression, builds off of this idea, right? So I always start with, like I said, motivate with something simpler, and then you can build on that. Perfect. So linear regression is what you use if you have, you want to predict, like the name suggests, a regression task. And if you remember, regression task is if the label you're trying to predict is numeric, if it is a number, right? And as I already said, because it's on my deck when I was preparing it, if you're trying to predict house prices with, say, one of the features you're trying to predict is the number of bathrooms, right? This is what you're trying to predict. This is your y-axis. This is your x-axis, right? So, like I said, you need data, right? When you're building ML models. So we've collected data on, so each of these red dots here are data points we have collected. So we've gone to, we know we've spoken to people in an environment, right? And we're like, oh, how many bedrooms do you have? 5. What's the value of your house? This. Obviously, it's not only the number of bedrooms we ask. We could ask for multiple features, more features to help us, because the more features we have, typically the better, right? So you have all of these points are different. Each point is a house, each point is a house, and it has a number of bedroom and house price, right? Now, if you look at this is a y, this is the x. You could draw a line between this that almost approximates this thing, right? Where you're like, oh, it kind of looks like it's linear, right? I mean, you could maybe put a line somewhere here. And if we do that, so we could put a line here, right? I'm going to bring this down here. You could put a line here, right? It's a bit off in some places, but it's not very far away from all of them. Maybe it's far from this one, sure. Right? So you could put one line here, right? And this is a straight line, right? This line has is of the form y equals to mx plus b, right? We can all agree with that because it's just a straight line in a plane. So it has its own slope. It has its own intercepts, which the intercept here, if we continue here, will probably be maybe 3 point something, doesn't matter, right? You could put a line here. You could put another line here. You could put another line here, right? You'd be like, okay, that's another straight line that you could draw. Or you could be like, this is another line I want to put, right? Or someone else may come and be like, you know what, actually, this is the line I want to put because this is the line I think makes sense, right? Obviously, this is a very poor line. It's not even close to the lines, right? So each of these lines, obviously, we could fit in, we could draw many lines. So you could put in multiple lines here. There are almost an infinite number of lines you could draw in this thing, right? And some of them are going to be closer to the data points that we've collected, or like this one is just completely useless because it's not close enough. It doesn't really approximate any of these things, right? Does that make sense? So obviously this one is definitely not the line of best fit. This is a rubbish line because it's so far away from every point. But I mean, there's nothing stopping you from drawing a line like this and be like, yeah, this is what you think the relationship is, which clearly isn't. Because the best lines, well, the other lines we have on this plane have a positive gradient, right? It kind of looks like the more the number of bedrooms you have. I mean, this is a mansion, right? 175, maybe Buckingham Palace. But the more the number of bedrooms you have, the higher your house price. That's kind of like the gist. But what this line is telling us is, the more your number of bedrooms are, the lower your house price, which doesn't really make sense, right? That's why this line is not great, right? Cool, so we'll move on to the next one. So yes, we are now in the domain of equations, right? So a linear regression assumes there is a linear relationship between the features and the numerical labels. That makes sense, right? This is your label, what you're trying to predict, y, right? And it assumed that there's that linear relationship. And that's why we were drawing a bunch of straight lines, right? It was why we did not draw a curve, because that's not linear regression. It's in the name, linear, because it uses lines to learn that relationship between the features, in the data we have, between the features and the label, right? So this is literally, so when you were in school, you people have been data scientists for the longest time. When you were in math class, drawing line of best fit and all that, you were actually doing data science, well, in a way. So in machine learning, we usually write the equation as y equals to, well, b. Some people write it as w naught plus w1 x1. Right? It's basically just a rewriting of this. We put this here first. Instead of m, which is the gradient or the slope, it's now called w1, and x is x1. And I'll tell you why you now have these ones here. Like, why do you have one, right? So y is the label, is what we are trying to predict. In this case, it's the house price. B is the bias or the y-intercept, right? Sometimes written as w naught. And I said, obviously, the bias or the intercept is where our line crosses the y-axis, right? So if I go back to this slide, each of these have different intercepts. This one also has a different intercept, right? And the intercept obviously determines where it starts on our plane, right? So W1 is the weight of the feature X1, right? Now, this is the most simple form of a line, right? And it's because it's just in 2D, XY. In ML, we don't really work in 2D, right? You have a lot of features that you're trying to use to predict a label. So you have number of bathrooms, number of bedrooms, the total size of the house in square kilometers. Those are the different things, or square meters, I say square kilometers. Those are the different things you can use, the different features you want to use to predict your label, right? So each of those ones is represented as an X because that's the feature. right? So W1 is the weight of the feature X1. And each of those features, they have weights, right? And weight is, it just basically tells you how much impact that feature has on predicting the label, right? It's just like, yeah, there are some features that will predict the label better than some, right? So the weight will control that, right? Now, so this is, for example, a more complex equation. So this is your bias. This is the weight of X1, of the feature X1. This will be the weight of feature X2, all the way to the weight of feature Xn, because you could have n number of features, right? Now, so training a linear regression model really is you are trying to find the good values for the weights and the bias or the y-intercept from labeled examples. That's what we're trying to do. So essentially what that means, let me quickly go back here. Essentially is because each of these obviously have different weights or slopes or gradients, the W's, and different intercepts, which is the W0 or the bias, which is B, right? So one of these lines will be, one of them is better than the other two. This one is obviously a useless candidate. So it's the worst of them, right? What we're trying to do is we're trying to find the weights and the bias that when we have that value and we plot it on this graph, it's going to be the best approximation of these data sets we have, kind of, right? So yeah, so that's why we said we're learning. So training in essence is just looking for those values, trying it, right? So in supervised learning, a machine learning algorithm builds a model that minimizes loss, right? So loss is a penalty for a bad prediction, right? There's a penalty for a bad prediction. So loss is essentially a number indicating how bad the model's prediction was on a single data point, right? So if the model prediction is perfect, the loss is 0. Otherwise, the loss is non-zero. Again, I'll go back to that deck to use it to explain what loss is. So actually, I don't have to. Actually, let's go to the next one. Yeah. So loss is the penalty for making a bad prediction. So I'll go to the next slide. There's a good deck here. Right. Look at this data point, right? This is your Y, this is your X1. We're using X1 because it's easier to do. As you go into more higher dimensions, it's harder to visualize. But obviously, this concepts transfer over to even higher dimensions, right? So the goal of training a model is to find a set of weights that have low loss across all the training data points, right? These are the data points we have here, for example. And someone put a line here. It's like, this person is like, yeah, you know what? This straight line is what I believe approximates this relationship, which obviously is a bad choice. Obviously, this has the y-intercept is somewhere here, and it has like a flat gradient or 0 gradients, right? So what you have here, so the loss is basically, like I said, the loss is a number that penalizes bad predictions, right? It tells you how far off you are from actually predicting what you're trying to predict, right? So this line is saying that if your value of X1 is maybe here, your value of Y is here, which is not right, because from the data we have, the value of Y is actually here. So the loss is actually the distance between the label itself, what we know as the ground truth, that's what we call it. What we know is the real value and the predicted value that the model is giving us. So look at how high this is. This is also very high. This is very high. This is quite, it does well here just by chance, because this one is actually close. This is high and this is high, right? So this is the loss for each of these training examples are quite high. If you combine them, this will give you a very high loss. On the other hand, you have a model here, right? That the loss is, it kind of approximates the relationship between the Y and the X quite nicely. It's not perfect. It has to sit somewhere, but it approximates. The loss is quite low, right? So you have something, it's quite short, right? So the general loss, this one is almost no loss. It's almost perfect prediction, right? So the loss here clearly is better than the loss here, right? So the goal really, when we say we are training a model, what we're trying to find is a set of weights, or in this one, it would just be whatever this gradient is, that's the weight, and whatever this intercept is, because those two things control where this line sits on the plane. So we're looking for the weights that give you low loss across all the training data points. Does that make sense? So that is the whole essence of training. Honestly, in machine learning, typically supervised learning, what you're trying to do is you have some data and you have a loss, something you are trying to keep track of bad predictions, right? That is how you know how well your model is, that loss, kind of, right? And the whole essence of machine learning is you are trying to find a set of weights, right? So now you could do that manually if you have all the time in the world, right? You could just be like, oh yeah, you know what? Can I draw another line here, maybe here, and see what loss you have, and see if the loss of that one is better than the blue one we have here. So you could try many different lines yourself, manually do it, manually calculate the loss, right? If that's what you want to do. Or you could use something we will get into in the next few slides. Right. So like I said, linear regression uses a loss function called squared loss, and it is the difference between the ground truth and the prediction, which in this case, this is the ground truth. This is for the data point, we know its real value, but this point on the line is what our model is predicting, right? So this is the predicted value from our model, because our model can never be perfect. It's just an approximation of the relationship. It just learns a relationship. It looks at them like, kind of like the general relationship is this, right? It kind of applies to everyone. So our model is essentially trying to kind of please everyone in a way, right? So the squared loss is the difference for linear regression, particularly. It's the difference between the ground truth and the prediction, right? So this is the ground truth or the observation. So the difference between them, and you square it. And the reason you square it is you don't want negative, you want just absolute values. You don't want maybe negative value to cancel out positive value. So you just square it, right? That's why you square them. In math or in textbooks, our observation, our ground truth is typically labeled Y. Predictions always have this cute little hats on top of them. And it's all the hats. So the predictions are called Y hats, and you square that. So that is the loss we use to measure how well our model does, or how well our line, which is just our model, does, right? So instead of when you eyeball, instead of just eyeballing and be like, this one is, we could eyeball this, we could look at it and be like, yeah, we know that the loss here definitely is going to be higher than the loss here, right? Definitely, just looking at it, right? But the squared loss gives us a number we can use to quantify the difference. We can use to quantify how bad the model is or how good the model is. Now, keep in mind that I said loss is for one data point, like loss measures the prediction on one data point, right? But in our training example, in our training data sets, what we use to learn that relationship, we will have, obviously, each data point will have its own loss, right? So you typically calculate the average over the whole data set, over your whole data set. And that's why it's called the mean squared error, MSE. So you hear something called MSE, mean squared error. And it's the average squared error loss over the whole data set, which is 1 over n, the summation of all of this. So you just sum all your loss together and you can find the average. This is what this means, by the way. This is just average, right? So it's In textbooks, some people conflate loss and cost functions, but they are different. Loss is for a single data set, a single data point. Cost is the average across all the data sets, across the data sets you have. Right? So for regression, we use squared loss or MSE as a cost function to actually just see how well it does. Right. So keep in mind that you obviously have data, you've collected data, you need data to train stuff, right? To train your model. Right? There are two types of data broadly. There's something else called the validation sets. We're not going to go into that in detail now. When you read textbooks, it will become clear why you have something called a validation set. But for this class, we're only going to stick with something called training and test sets. As the name suggests, the training set is the data the algorithm actually uses to learn the underlying patterns and the relationship in our data sets, right? So I go back a few decks. All the points here make up our training data set, our training sets, right? So when you collect data, right, and you're trying to train a model, you have to split your data into broadly two types of data sets. The training data set here, which is this blue one here, which you see is the majority, and the test set, which is this, is this yellow, maroon? I don't know. No, it cannot be maroon, of course. Whatever that color is, I'm not good with colors, but yeah, blue is very easy to identify with me, for me. So you split it into training sets and the test set, right? So the test set, by the way, has to be kept completely independent from the training data. The test set should not be put into your training data, right? You should not use it to train your model because it is actually used to assess your model's ability to make accurate predictions on data it was not trained on. What's the difference between test set and validation set? So test set is something you always keep separate. Like at the start of your training, you split your data, bam, bam. Training here, test here. You keep your tests separate. It is when you finish your whole model development process, you want to see how well your model does, right? And I'll give an analogy for that. The validation set is really another set you keep apart sometimes that you use for something called maybe model fine tuning. Yeah. Maybe you want to try different configurations of a model, right? You want to use the validation sets before you actually then see its final performance on the test set. You want to use that validation set to test the performance of the different configurations of your model, right? The reason I left it out of here is because I did not want to complicate this more than it needs to be for an introduction to machine learning course. But yeah, so you have the training set and you have the test set. Typically, you have them split 80-20, 70-30. You find it in textbooks, depending on how much data you have. But the training set is larger than the test set. So yeah, so I'll tell you why you keep test sets separate, because I think analogies help things stick, right? So I'll give you an example. When you are in school, when we're in secondary school, you do your internal exams, getting ready for WAEC or NECO or whatever we did, or people that did outside exams, right? You in school, your teachers give you data, you learn, right? But the ultimate test, so the ultimate test of your learning is when you go out there to WAEC, to an exam that was not set by your teacher, who you probably know is techniques, you know everything about them, you know how to ask questions. You can maybe maybe your teacher sometimes will come to class and give you, oh, you know what, this is the areas to concentrate on. So yeah, the ultimate test of how well you do, of how well your training is how well you do on a test, on an external test. And that is the analogy I always use for a test set. That's why you keep it independent. WAEC is an independent body because no school, ideally, can actually tamper with it. So they bring a test, they're like, oh yeah, let's see how well you've learned. You said you've learned these things. Let's see how well you've learned. So that is what the test set is. The test set is the WAEC of machine learning, in a way. That's if you want to see it that way, right? It's what you keep independent, you keep separate, right? And that's really what we do. That's train and test. So I'll go to the next one. Perfect. So that was a quick description of, train and test it before we go into reducing loss. Because keep in mind, before this slide, I spoke about the goal is to find a set of weights that have low loss across all the training data sets, right? So you want to find, there are many lines you could draw into this thing. You could draw many lines, right? So iteratively, you want to find the one that gives you the lowest loss, right? So what you do really is you begin your training by starting with an initial guess for the weights and the biases, and you iteratively adjust the numbers until we get weights and biases with the lowest loss. So what I'm doing here is you have your features, your number of bathrooms, your number of bedrooms, all those things, your label, which is the house price. Your features go into your model, right? You make predictions, which is that line. So so your model can say if a house has 2 bedrooms and maybe 2 bedrooms and 1 bathroom, house price is 10 pounds, But in the real data set, our real observation is maybe 15. We know that the loss will then be 15 minus 10 squared for that particular data point, right? Which is 5 squared, which is 25. So you do that, you compute the loss, and then you update the parameter, right? You update the weights and the biases. By update, you want to reduce it because you're like, yeah, this is quite high. I want to maybe reduce it. How do I reduce it? It's this iterative process. So this grain field computes parameter updates. We are going to actually see how that's done in machine learning, right? But what happens is you have your features, you pass it into your models, your models obviously make certain predictions on your training sets, right? Or your validation sets in some cases. You compute the loss or the costs, the average loss across all your gen examples. And then you update the weights and the biases. You want to be like, yeah, this is not good enough. This weights, maybe you started with this weights, this type of useless model. Maybe you started with something like this, right? When you calculate the loss will be very high. So you want to change it. You want to update the value because you're like, yeah, this is not a good value. Give me new values that are better, right? And then maybe ultimately you arrive here at a line that is this good. So that is what this iterative process does for us, right? Does that make sense? That makes sense. Okay. So gradient descent is the model we actually use to do that parameter update the weights and the biases, right? So it's an optimization algorithm. Again, supervised learning is really just optimization of some function, right? It is used to minimize our loss function. The idea is to iteratively adjust the weights of our model in the opposite direction of the gradients. And that was why I was saying of the slope. That was why I was asking us, oh, what's the gradient here at that start, right? Because if you know the gradient really points in the direction of increase. Keep that in mind. The gradient points in the direction of increase. So when you calculate your gradient, right, it points you, if you want to go up the steepest, the gradient will tell you which direction to go. Typically, it's a vector. Right? I know you did linear algebra, was it last week? So what gradient descent does is, for the new value of the weight, when you want to compute the new value of the weight, imagine if you started with the weight of that ugly line, right, or something like that. What gradient descent does is it subtracts the gradient, right, the product of this alpha value, something called alpha, yeah, product of the gradient and this alpha value, it subtracts it from the value of the current weight we have. That is not maybe a great value, right? Again, what gradient descent does is it takes the current value of the weights, and from that, it subtracts the product of the learning rate, which is this thing, which I'll explain, and the gradient of the loss function from from the weights, right? And keep in mind, the reason why it does that is if you want to minimize a function, right? If you want to minimize a line, you find the gradient, and the gradient tells you, oh, if you want to go up, go in the direction of the gradient. So if you want to go down, what do? You go in the opposite direction, right? Because you're trying to minimize something. You're trying to go to the bottom. You're trying to go down, minimize. The gradient tells you which direction to go up. So cleverly, you're just like, oh, I don't want to go up. I'm just tricking you. Just tell me. So you tell the gradient is essentially saying, tell me which way I have to go if I want to go up. And it tells you go up that way. So you just know that, oh, I just need to follow that line down. And that's what happens, right? And how far this thing controls is a hyperparameter. So your W1 is the current value of your weights. Your W1 plus 1 is the updated value of the weights and the biases of your parameters, of your model parameters. I'll just call them model parameters going forward. Alpha is the learning rate. And basically it tells you how, so you know when gradient descent is which direction should I go, and I'm going the opposite direction, it tells you how quickly you should go in that direction, right? You could get, maybe you don't trust it, you get eager and be like, you know what, oh my God, I now know I have to go in the opposite direction. Let me jump. That would be a very high learning rate. I want to jump. I'm so excited. Or you could be like, you know what? Let me be cautious. Let me take a very slow step because I'm on this very steep slope, and I don't want to fall off because I'm scared. So let me take small steps, right? Or you could just take assured steps, right? So this parameter alpha here controls that. It's called the learning rate, right? And this obviously is the gradient of our loss function. Does any of that make sense? Analogies, all that. Does it kind of click?
Yeah, so sorry, there was one analogy you're trying to give, like when gradients, like when you have the slope,
yeah,
that you have to follow. I didn't really get what you were saying, like following.
Okay.
The
so
direction
you get it now. So look at this bow. Look at this bow, right? This is our y-axis is the loss. Obviously, the loss here is high at this point here. At the top here is high. The loss here is high. And this is obviously the x-axis is the value of our weights of the model parameters, right? Of the line, right? Here is the best place because this is the minimum of this loss, because where the value of y here at this point is the one that gives us the lowest value of the loss, right? So if you want to calculate a gradient, the gradient at any point in this line, obviously you draw a tangent line, you calculate the gradient. And what you're trying to do is the gradient will tell you if you want to go up, which way should you go? So imagine if we start from here, right? You start from here. And the gradient will tell you, oh, if you want to go up, right? If you want to increase this, if you want to go up, because you calculate the gradient here, it's going to tell you to move up here, right? But you don't want to move up, you want to go down, you want to minimize this, right? So you subtract, you go this way. So you're like, oh yeah, I don't want to go up. The gradient will tell you to go up, but I want to go down. And this is then where you go. Does that make sense?
Yeah. Thanks.
So exactly. So you calculate the gradient at a particular point. So this obviously, like I said, it's randomly initialized at first. You just basically pick a weight. It could be a poor one, and then you iteratively change it by calculating the gradients. The gradient tells you go up. You're like, oh, I tricked you. I'm going down actually because I'm not trying to go up. Well, I'm trying to go up in Jesus' name. I'm not trying to go up that slope. I am trying to go down the slope, right? Down the surface. So you go in the opposite direction of the gradients, and that's what you keep doing, right? And like I said, the learning rate controls how much of a step you want to take, right? So the learning rate is a hyperparameter. There's a difference. I highlighted it because I want to talk about the difference between a model parameter and a hyperparameter. So the learning rate is one of the most popular hyperparameters that determines the size of the steps taken at each iteration when updating the model's parameters during training. So the model parameter in our case are the what? The weights and the biases, right? Those are the things we are trying to learn from the model. That's the parameter of the model we're trying to learn. The hyperparameters control their parameters not within the model themselves. they control, they are like knobs, they're like things you tune. So imagine, I don't know, I'm going to expose my age now. I don't know if you know some televisions at some point. When I was younger, there was my grandfather had this old TV where if you wanted to change channels, right, it wasn't where you could just get a remote control and just flick it on and play like one or two. They had knobs that you could turn, right? Or even radio. Let's use radio. I think all of us are old enough to know radio. If you want to go to certain radio stations, right? There's this knob on top of a radio of a radio player, where you turn it. Sometimes it doesn't give you good. It doesn't catch any station, but you keep turning it until you get the desired thing you want, right? That's a hyperparameter. A hyperparameter, like learning rate, just controls the process. It's not the parameter itself you're trying to learn, right? So the learning rate here determines the size of the steps taken at each iteration when updating the model parameter, right? So you start from here. So like I said, you could choose a small learning rate, because if you choose a small learning rate, you have been very tentative. After you've calculated the gradient, and the gradient tells you, go up this way if you want to go up, but you're like, no, I don't want to go up. I want to go down this slope. You could take a very big step, or you could take a small step. If you take small steps, you're going to take forever to actually get to the bottom here, right? Makes sense, because you're taking very small steps. Like you're just scrolling because you're scared. On the other hand, if you take very large steps because you are too excited, if you start from here, gradient tells you to go here, you take such a big step, you go from here, bam, you jump here. The next one, you go from here, you jump here, you've overshot this place you are supposed to be, because you were very close to this place, weren't you? But because you were just still excited, you took a very huge step, and then you rolled across the minimum you are trying to get to, right? So Dolamu said, I think taking small steps is suitable. It's not. It's going to take forever, and you don't have time. So Shea said, this sounds more like backward propagation in deep learning. It's basically gradient descent. Yes. So I like how you people are giving me. I'm happy that this is happening, because it shows that you actually get it. So small steps will make your training run forever, because before it gets to the minimum, it could take all the time. If you have too large a step, it's just going to be bouncing everywhere, because it's not going to settle down, right? The best one, Dalamu, is actually when you have a learning rate that is just about right? That makes sense. It's not too big, it's not too small. Right? So you just go gradually, until you get to the minimum. Now, for the sake of this, there are many ways to actually do this, to set the learning rate, to optimize it, and all that kind of stuff. We're not going to get into that on this course, in this class. But I hope that when you pick up a textbook, or when you pick up a book, the intuition behind what's happening with learning rate and all that will help you understand the math or whatever comes in. Does that make sense? So Dolamu, taking small steps is not really suitable. It's finding a nice learning rate that is not too small, that's not too big. That's just somewhere in the middle. But is there a possibility it never converges to a minimum? Yes, it's very possible. There are many things that could happen. So this function, for example, is very easy. They call them convex surfaces, because you have just one minimum here. Very easy to optimize, very easy to go down the hill. But in real life, where you have a lot of features, because we only have one feature here, like just one width. In real life, where you have very complex data sets with hundreds and thousands of features, your loss function, this thing, becomes a multi-dimensional surface. Multi-dimensional surface that is hard to actually picture, right? So it's possible that your ball that is rolling down this hill could get stuck in a suboptimal place, right? In a local minima, they call them sometimes, or something called the saddle point, and it just never leaves that place because it doesn't know how to leave that place. There are many ways to deal with that, but it's very possible that it doesn't actually converge to a minimum, right? So, and how would you know a suitable learning rate to use since scenario differ? Yes, a lot of research around that. Separate, if you're doing deep learning, there are certain tasks that if you read the paper, they tell you which learning rate to use. Typically it depends, honestly. Certain learning rates that's why you have validation set, where if you want to try multiple learning rates, you keep a validation set. You set a learning rate, train on that, see how well that combination of learning rates does for your loss. You try another one, you see how well that does, and then whichever learning rate gives you the best performance is the one you then use to train a full model. So there's a lot of ways to do it, right? But yeah, this is to just motivate the idea of learning rates. So yes, overfitting and something called regularization, which I will not talk so much about because we have 7 minutes in this class, 7 minutes left in this class. I do not want to, because I know we've covered a lot for an introduction to machine learning class. And I think where we are, it's a good place. So overfitting happens when our trained model does not generalize well to new data. It will perform what? I'm going to edit this. I'm going to explain what that means. I'm going to use that analogy of WIAC again. So in school, right? Maybe you, at the start of the semester, or what's it called? At the start of the term, when you start a school term, and they give you an exam at the start of the term, you probably, your result will probably be very poor, except you are a nerd that spends all your summer holidays just reading up textbooks, which many of us were not, right? So your result will probably be poor. So as your teacher trains you over time, and they keep testing you, you know how you do all those little tests, hopefully your performance, your loss, how poor you are with the questions will reduce, will keep reducing as iterations go, right? So on your training data, so when you fit a model, you want to check its performance on your training data, right? Obviously, they'll test you internally, right? So typically, you will do very well, hopefully with time, if your training thing is done well. Now, imagine if you could take WIAC every time, imagine if you could take WIAC every time you are also taking your internal exam to test, right? Just imagine that was a thing, right? But every time you take WIAC, right? At some point you start poorly too, because it's the start of the term, you have not really prepared. And at this point, when you are doing very well on classwork, right? On your school's exam, but somehow you keep failing WIAC. Like the distance between your results in your internal exams and the one that is set by external invigilator by WIAC is so you're doing so poorly on WIAC, right? So what does that tell you? Can someone just come up mute and tell me, what does that tell you? If you're doing so poorly, you're smashing your school exam, but you go to WIAC, you are failing your hand. What do they call people like that? Is it not local champion? So can someone get up? What does that mean? What does that mean to you?
So I think it means that the questions they are setting for the school exam is quite different from that of WIAC. So when the person in question sees the question in WIAC, it tends to follow.
Yes, that could be a thing. That's a very good one, because yes, it could just be like what they are teaching you in class does not cover the whole, is not representative of the type of questions WIAC will ask you. So your school is not teaching you well, right? So your training data is not representative of the population of what people typically should be asked, right? So that's a very good one. I like that. Who wants to say something else? What could be the reason why you're smashing your school exams and every time you go out there, you're just not doing well? What could be the reason? In your own words.
Hello.
All right.
Okay.
Yep.
Okay. So what if the school exams, the questions are just repeated? You understand? You're not actually learning, but the questions are like repeated year after year, time after time. And so
Yep.
it's just like second nation to you.
Yeah,
Why
exactly.
you actually have to think about it.
Yes, exactly. So that's what overfitting is. Overfitting is when you have a training set, right? And your model has learned everything about that training set. The relationship between the training set has learned it so well, but it hasn't actually learned anything useful. It cannot generalize to other things outside of that training set, right? So it's not very useful, because if you cannot do well on something, you should do well on something that should be representative of what you've learned, right? If you've really learned something, someone should be able to tell you, oh, what does this mean? Even if you've not seen it before. If your knowledge is good enough, you should be able to answer it, right? Would you agree with me? Right? So that is what overfitting is really. It's when your model does not generalize. That's what they call it, generalization. If your model doesn't generalize well to new data, to unseen data, and that's why you keep your test set separate. You don't want to pollute it, because if you put the test sets into your training, you're basically cheating, right? There was a year, I'm sure it's happened before, where WIEC questions were leaked and they had to cancel things, because obviously if questions are leaked before, then your training is, you just need to basically cram the answers and just go in there and write it down. So you're not really testing things, right? And that's why you keep your test set separate, right? So this is validation. When you are training a model and you see and you plot your loss metrics like this for your training and your test set or your validation set, and you see something like this where there's a huge divergence between your training error and your validation or test error, then your model is overfitting. So you need to go back and then be like, yeah, there are a lot of techniques you could use to then be like, yeah, you people are not learning anything. We need to fix that. And that's one of the techniques for that is regularization. And it's basically saying you want to penalize your model for learning too much about just that training set and not trying to learn outside. So your teacher will be like, so regularization is just basically your teacher saying, no, you people have not learned enough. You are just cramming this thing. Explain this thing to me in your words, right? That's basically what regularization is in a way, right? So there are different forms of regularization, right? There's something called L1 regularization. You find it in textbooks. I did not bother to cover it here because it's long. Something called L2 regularization. It's basically ways of making sure the training process doesn't just overfit on the training set, right? So that is training, overfitting, regularization. There are many ways to make sure your model doesn't overfit. It's huge sections and textbooks are dedicated to that.
Hi, okay, so if we're using linear regression, for example, I believe it's meant to be a line being fit on the data point. But in the case where overfitting is happening, I believe overfitting is when it's understanding too much details about the data, right? So it's trying to make the data points fit into each other. So imagine it in my head, I don't think it would be a straight line. I wanted to be sure if it's a straight line or not, because if it's a straight line, it's not trying to fit each of the points. It's just a straight line. I don't know if you get what I'm saying.
No, I think I get it. So you're saying if it's a straight line, it's not possible to overfit. So let me say, let's go back here. So linear models, linear models are unlikely to overfit, right? So overfitting will typically happen if, I did not want to cover non-linear stuff, right? Because again, that's just complex. We're already at the end of this class. Look at what we've covered. You have linear models that just assume, like linear regression, that the relationship between your features and your label is just a straight line like this, right? That is the fundamental assumption of linear regression. No matter what the actual relationship is, right? Even if it doesn't look linear like this, linear regression will still assume that, you know what, I'm going to approximate this relationship, no matter how complex our relationship is, with a linear line, with a linear line, yeah, with a line, right? So for that, because it makes that very simplistic assumption, it's unlikely. It could overfit, but it's unlikely to overfit, right? A case where it could overfit is, imagine if this is your training data, right? But you have a test data that looks nothing like what is in the training data set. Like the training data set and the test data set are completely disjointed. They don't come from the same distribution. They don't look alike. Your model will not do well. It will overfit, because it means that it will perform very well on your test set because it looks a certain way. And if it comes to trying to infer on a test set that doesn't look anything, that's from a separate distribution from your training set, it's going to perform poorly, even as it is a straight line, right? So you have non-linear methods of doing regression, where instead of maybe having a straight line like this, you have a more curly line that could maybe just snake around and could capture more complex relationships. And those have a tendency to overfit. I mean, I'll share a blog post I wrote a few years ago. It's called, I think, Demystifying the Bias Variance Trade-off, because the question you're asking me now then leads into something called the bias variance trade-off. I will share the link to that, and I think you will get better answer at the end of this class if you read that, because I also try to write in rather simple terms there. So hopefully you get to understand that. If you don't, send me a message on Twitter, or just ask me on Twitter, and I will try to explain after. If you try to do that and you still don't understand it.
So my question is on mean square error. I noticed you talked about square mean error, square mean error, or square mean loss.
So let me get that. I didn't. Yep. I think it's here. Yep.
So my question first, so mean square error, the same as mean absolute error.
No, they're different. So it's
okay. If they are different, most materials I've read so far, mean absolute error, and they hardly touch on mean square.
Yeah. So I mean, it depends. Again, it depends. Both of them are loss functions, right? So mean absolute error, the difference is, look at that, mean squared error, and the other one is absolute error. So with squared error, the difference between your observation, the ground truth, and your prediction, you square them, right? And the absolute value is you just calculate the absolute value. So if you have, it's just going to return a positive value every time. So if you have -2, it turns it into 2. If you have -5, it turns it into 5. If you have +5, it turns it to +5, right? That's the absolute value, right? The difference is rooted in statistics, in something called outliers, right? If you have huge values, outlier, right, and your model maybe predicts, so if you have an observation that's maybe 100,000, right, and your prediction is maybe 1,000, the difference between those two things is what, like maybe 90,000, right? I don't know, but something like that, right? So 100,000 minus 10,000, difference between that is like 90K. If you square that, right, that is a very huge number. It balloons because that's an outlier. That's just a very big number, right? So it affects the total value of your squared loss, right? So the reason some people favor MAE, which is mean absolute error, is because square of anything is susceptible to being ballooned by outlier value. So if you have a very huge value, if you square it, obviously you're just going to double that. Absolute error doesn't deal with that, because absolute will just take the difference. While it's still a huge number, it doesn't square it. It doesn't compound the mistake, basically, right? So that's the difference. You can use both of them, but the MSC is kind of easier to use, because if you're calculating the gradient, because keep in mind that you calculate the gradient of our cost function relative to the parameter, it's easier to calculate the gradient of MSC because it's kind of easier to do than an absolute. Because square, you can calculate the gradient of this rather easily. if you want to do that by hand. So that's the difference, right? MAE, MSC, outliers, ballooning, outlier values, and all that. Make sense?
Yeah. So basically, I'm just asking that now in overfitting, how can we prevent now overfitting?
How can you prevent overfitting? So it's with something I called regularization, which we discussed here. Let's see this. So it's called regularization. And I did not cover it here deliberately because I did not want to complicate this even further, but I just wanted to motivate it. So regularization is, we have two types really. Well, in this closed domain we are working on, L1 regularization and L2 regularization. And it's basically a penalty term that you apply on your training process. You basically say, it's like, if I go back to the example of school, it's your teacher basically telling you, oh, I know you people are not learning anything. You're just cramming this thing. We are going to actually I'm going to make sure you are learning things. So your teacher may ask you, so if you say 2 + 2 = what? And you have like 4 because you crammed it, you know that. And your teacher is like, okay, why is 2 + 2 = 4? What is 1 + 1 + 1 + 1? Which is should be 4, right? So your teacher wants to test your understanding. So that is basically, your teacher is regularizing, in a way, your training, your thinking, so that the teacher can be sure that you're actually not only cramming what is in the training, what they've taught you, but they want to make sure when you can reason beyond what they've given you, you've actually learned the process of calculating sums in this case. So if your teacher was to ask you 1 + 1 + 1 + 1 + 1, and you don't do well, then your teacher knows you're not doing the right thing. You don't get it yet. You know 2 + 2 = 4, but you don't know that when 1 + 1 + 1 + 1 + 1 = 4 also, then there's a problem. You should know that, right? So your teacher will tell you, oh, you know what? There's a problem, so we need to train you again. So that's regularization in a way. That's it's just it's the way I loosely put it. Does that make sense?
Yeah, and besides that, can we talk about the hyperparameters, the choices of hyperparameters like the learning rate? Can that one also can it result to the overfitting?
Absolutely. I mean, everything in the training process could, because your learning rate could affect, it could underfit, in fact. So there's something called underfitting when you don't even learn anything. It's just a useless model. Like that ugly line we had is an underfitting model, right? So depending on your learning rates, if your learning rate gets stuck, maybe you keep maybe you use a very small learning rates and it gets stuck somewhere here, you stop your training here, this will underfit, right? It will just be like, oh yeah, I'm not learning anything. So it depends. Like, so your learning rate definitely affects what you have, like the value of your loss on your training set. And when you test it finally, because obviously your learning rate controls what the value of your parameter will be, right? And it's the value of those parameters that will then use to make inference, right? So your learning rate controls where it will eventually land, and ultimately controls what your training error will be and what your validation or test error will be. So yeah, it does affect it. Make sense?
Okay. Yeah. Thank you. I don't know. I have one last question.
Oh, it's fine. Yeah.
I don't know to give room for others. Okay.
Does anyone? So hold on, Jack, because I'm conscious of time. I know you're going to start your labs. Does anyone have any question? If anyone doesn't have any question, we'll take one final question. If anyone doesn't have any question now, someone else, then you can ask. If not, shoot me a message on Twitter. Does anyone have any question outside? Oh, no lab today. Oh, okay, that's good. Well, I'm going to cycle, so I need my time also. Does anyone have any questions? If not, the floor will allow Jack ask his question. And also, I mean, I put my Twitter. This is where I talk and just opine about things that don't really concern me. So you can send me a message. But when I say message, I don't mean a DM, because it's unlikely I'll read that, because it always goes into like the other part. Just ask me, and I'll try my best to reply when I can. So I don't think we have any more questions. This has been an absolute delight. Thank you so much for having me, everyone.